Artificial intelligence isn't just software anymore, it's a new industrial force. Training GPT-4 reportedly used as much electricity in weeks as 120,000 homes do in a month. But here's what most people don't realize. The costs aren't staying in Silicon Valley. In parts of the US, regulators say data centers caused more than 60% of last year's electricity price increases. In states like Virginia and Ohio, household bills could climb 30 to 60% by 2030. Not because you turned up your thermostat, but because AI servers are running non-stop. By 2030, AI data centers alone could consume more power than Japan. The question isn't just whether governments and utilities can keep up, it's whether your own bill, your city, and your grid can survive the AI boom. It's not just your neighborhood. Globally, the numbers are staggering. The IEA projects data center electricity demand will double by 2030, hitting nearly 1,000 terawatt hours annually. That's like powering South Korea for a year, just for server farms. The epicenter is Northern Virginia's data center alley. It already consumes 25% of the state's electricity. New requests exceed 4.5 gigawatts, more than all of New Zealand's demand. Ireland is facing the same squeeze. Data centers there already account for 21% of national consumption, and EirGrid projects 40% by 2030. Each new wave of AI workloads is the equivalent of adding a small country's power demand overnight. Now, to really understand the stakes, we need to unpack where all this energy is going. Because AI workloads aren't all the same, and the difference determines whether this is a short-term spike or a permanent burden on your grid. Think of it like this: training is the boot camp. It's huge, expensive, but one-off. Training GPT-4 cost an estimated $78 million in compute and electricity. Like building the airplane, painful, but it happens once. Inference, on the other hand, is every flight the airplane takes afterwards. Every chat, every Copilot command, every AI agent, millions of times a day. That's the forever meter running, and it's already dominant. UBS estimates inference consumes 10 to 15 times more power than training over a model's lifetime. One ChatGPT query uses 10 times the power of a Google search. Multiply that by billions of daily prompts, and you see why inference, not training, is the real driver. It's gotten so real that OpenAI's CEO Sam Altman recently asked users to stop replying with simple "thank you" prompts. Why? Because even those tiny, polite inputs still spin up GPUs, adding to the energy bill. When you scale that across hundreds of millions of users, the waste becomes staggering. The IEA projects AI-specific data centers will quadruple their demand by 2030, with inference as the main force. And companies know this. OpenAI's GPT-4o Mini was built to cut inference costs and energy intensity. Nvidia's Blackwell GPUs deliver 30% more throughput per watt. And new systems like Manus AI agents run continuously, adding load even when no human is typing. Training is a surge. Inference is the permanent electric bill. But grids weren't designed for this, and the stress is already visible. In the US, many transmission lines are 40 to 50 years old, far past their original design life. These lines were built when the internet didn't exist, let alone AI supercomputers. And building new ones isn't quick. Permitting and siting often stretch projects to 7 to 10 years before a single pole is raised. That means demand is rising far faster than supply can keep up. And it isn't just electricity. Data centers also need cooling water in addition to electricity, in some cases millions of gallons daily, equal to the usage of tens of thousands of homes. In drought-prone regions like Arizona and Nevada, this is already sparking fierce debate. Who should get priority? AI servers or families and farms? Case in point, in the PJM grid region, covering Virginia, Ohio, Pennsylvania, and more. Data center demand has already pushed wholesale power markets higher. One report found that data centers drove over $7 billion of recent capacity costs, directly affecting what consumers pay. Consequently, utility customers across 7 PJM states were billed $4.4 billion last year just for transmission upgrades tied to hyperscale centers. Analysts now warn that residential bills could rise 30 to 60% by 2030. Some households are effectively paying a hidden AI tax of up to $27 a month to fund these expansions. And this is not just an American story. In Ireland, data centers already consume over 21% of national electricity, headed toward nearly 40% by 2030. Dublin's grid operator has paused new data center approvals until 2028 to prevent blackouts. Other countries are facing the same squeeze. The Netherlands briefly froze new permits in 2022 over land and water concerns. Singapore capped approvals after data centers began straining its small island grid. Even in the US, Texas regulators have raised alarms about whether their system, already tested by winter blackouts, can support the wave of AI facilities. This isn't just about trillion-dollar companies racing for AI dominance. It's about whether your monthly bill, your water supply, and your grid become collateral damage in the AI arms race. But when value shifts this violently, it doesn't just destroy, it also creates. Some players are emerging as clear winners, others are scrambling to respond, and many are left carrying the risks. To see where this is heading, we need to map the AI energy value redistribution. These are the winners, players capturing value at the front lines. First, utilities with firm baseload, such as Hydro-Quebec's hydropower, France's nuclear fleet, and other utility operators. These are being rebranded as strategic power hubs, not legacy assets, especially where clean, stable power is scarce. Then comes energy storage, the hidden kingmaker. Tesla deployed 31.4 gigawatt hours in 2024 across Megapack and Powerwall, doubling its previous year. And in Q2 2025, it added 9.6 gigawatt hours in storage systems. Their new megablock architecture pledges to deploy 1 gigawatt hour in just 20 business days, a game changer if it scales. Fluence, already with 6.3 gigawatts deployed, holds a strong backlog and just opened a 35 gigawatt hours factory in Vietnam to scale globally. These companies are not just building storage, they're becoming the gatekeepers of flexibility, the buffer between AI's appetite and grid stability. Third, chip and efficiency innovators. Nvidia's data center arm hauled in $22.6 billion in Q2 2025, demonstrating demand for efficient compute. Startups like Furiose AI promise H100 level performance at 1/3 the power draw. That's a potential shockwave in a world where inference cost matters. In short, utility plus storage plus chip efficiency equals the new energy trifecta in an AI world. And then there are those who bear the hidden costs, often without realizing it. In the US PJM grid, billions in new data center capacity costs are already flowing through to ratepayers, with household bills projected to climb 30 to 60% this decade. It's not just money. Every megawatt of AI compute requires 3-5 tons of copper wiring, adding up to more than 1 million tons of new demand annually. And in drought-prone states, water-hungry cooling systems are already colliding with farms and families. These are the risks buried behind the shiny AI narrative, externalities now crystallizing for societies, utilities, and consumers. Those externalities aren't just social or environmental, they're financial. Because when entire grids strain under AI's appetite, capital doesn't retreat, it floods in. From utilities to chip fabs to power metals, money is chasing the AI energy boom like it's the next gold rush. And the numbers are staggering. McKinsey estimates the world will need $6.7 trillion in new data centers by 2030. Deloitte projects another $1 trillion in US AI infrastructure by 2029. Google is spending $75 billion on AI infrastructure this year. Microsoft, $80 billion. Combined, the top 4 hyperscalers have pledged $364 billion in 2025 alone. And investors are following that current of money, betting on the supplies of power, storage, and stability. In nuclear, utilities like Constellation and Vistra are quietly becoming power brokers again. Their clean, firm generation suddenly the rarest commodity in tech. Startups like Oklo are advancing small modular reactors, promising distributed nuclear power for data centers before the decade's end. In renewables, NextEra Energy just beat profit estimates thanks partly to AI-driven power demand. Its renewables and storage backlog is now one of the largest in North America, proof that clean energy utilities are morphing into the landlords of the AI age. First Solar is signing multi-gigawatt contracts with hyperscalers, locking in predictable long-term revenue streams. In grid and infrastructure tech, ABB, Siemens, and Schneider Electric, once industrial mainstays, have collectively added over 150 billion euros in market value since the AI surge began, fueled by demand for electrification, cooling, and automation gear. And beneath it all, commodities are turning into leverage plays. Uranium prices are up nearly 70% this year, lithium is rebounding, and analysts estimate AI-related copper demand could top 1 million tons annually, enough to move global markets. But not everyone is convinced. Major banks warn that AI would need to generate $2 trillion in annual revenues just to justify this capital wave. Otherwise, what looks like an energy revolution could morph into something else entirely. A bubble, only this time is one built not on apps, but on power plants and grids. The AI revolution isn't just about smarter code, it's about electrons, copper, water, and the bills on your kitchen table. Will AI force a clean energy breakthrough, or will it snap our grids first? Drop your take in the comments. Which company, commodity, or policy do you think wins or fails as AI's power appetite explodes? If you found this deep dive useful, like the video, it really helps the channel grow. And subscribe to StratyQ for more strategic breakdowns of how technology, finance, and power intersect.